to all. I am Dr. SRINIVASAN, Chemistry Wing of DDE, Associate Professor. Especially I am handling physical chemistry. Now we are going to see thermodynamics in physical chemistry. Very simple chapter. If you are understanding easily, you can get full knowledge in thermodynamic system. Okay. Now we are going to see thermodynamics chapter. Unit 5 in thermodynamics. First we are going to see the basic concept and the first law of thermodynamics. Actually we are having that syllabus: definition of the system and surrounding, types of system, thermodynamic properties, intensive and extensive properties, state and path function, concept of heat and work, thermodynamic equilibrium, reversible and irreversible process. The first law of thermodynamics, especially in first law of thermodynamics, statement heat capacity at constant volume and a constant pressure, relationship between Cp and Cv. So finally we are going to see Joule's law. In Joule's law, Joule-Thomson coefficient and inversion temperature, after that calculation of W, Q and then energy enthalpy for the expansion of ideal gas under the isothermal adiabatic condition for reversible process. Okay. So first introduction. In thermodynamics, thermodynamics is a branch of science that deals with the quantitative relationship between heat and other forms of energy. It is concerned with the internal conversion of one kind of energy into another without destroying the energy. The transformation from one to another energy form and the prediction of the feasibility of the process are important aspects of thermodynamics. It is used to, actually object of the system, it is used to predict the feasibility of the process, to estimate the yield of products. It is used to relate the relationship between directly observable properties. It deals with the properties like temperature, pressure, etc. of the matter in bulk. It concerns itself only with the initial and the final state of the system and not concerned with the mechanism of process. To define the first law of thermodynamics, after that how to understand that application of first law of thermodynamics to deduce the relationship between Cp and Cv, to understand Joule's law and Joule-Thomson coefficient, to determine the Joule-Thomson coefficient of ideal and real gases, finally understanding of concept of inversion temperature. First, the content and terminologies in thermodynamics. Actually, we are going to see first system and surrounding. If we are considering the system, we may consider open system, closed system, isolated system. After that subdivision part of the system, generally homogeneous system, heterogeneous system, macroscopic system. Now we may discuss individually systems, the part of the universe chosen for thermodynamic consideration. The remaining portion of the universe excluding the system is called the surrounding. Open system. In open system may be defined as, or it may be said to be open system if it can exchange both matter and energy with the surrounding. For example, if some water is kept in open vessel, exchange of both matter and energy takes place between the system and the surrounding. Closed system. If a system can exchange only energy with the surrounding but not matter, it is called a closed system. For example, if some water is placed in closed metallic vessel, then as vessel is closed, no exchange of matter between the system and the surrounding can take place. However, as a vessel has conducting walls, exchange of energy can take place between the system and the surrounding. Isolated system. If system can exchange neither matter nor energy with the surrounding, it is called an isolated system. For example, if water is placed in a vessel which is closed as well as insulated, no exchange of matter or energy can take place between the system and surroundings. This constitutes an isolated system. Macroscopic system. Macroscopic system means a system containing a large amount of substance. In other words, a macroscopic system is one in which there are large number of particles, that is atoms, ions or molecules. And second part, homogeneous system. A system is said to be homogeneous if it is uniform throughout. For example, A gas or a mixture of gases or a pure liquid or a pure solid or solution of solid in a liquid are all homogeneous system. Such a system is said to have only one phase only. Heterogeneous system. If a system is not a uniform throughout, it is said to be heterogeneous. It consists of two or more phases which are separated from each other by defined bounding surface. A common example of heterogeneous system is a system consisting of a liquid and its vapor. Next, thermodynamic properties. Here we are going to consider extensive properties as well as intensive properties. So first of all, we are going to see extensive properties. These are the properties which is depend on the quantity of the matter contained in a system. Examples of the properties are mass, volume, energy, heat capacity, etc. The total value of extensive property is equal to the sum of the value for the separate parts into which the system may be divided into convenience. Intensive properties. There are those properties which depends only upon the nature of the substance and are independent of the amount of the substance present in the system. The common examples of these properties are temperature, pressure, refractive index, viscosity. State of the system. The state of the system implies a condition of the system when the various macroscopic properties like pressure, volume and temperature, etc. of the system have definite values. The first and the last state of the system are called initial state and final state respectively. The state variables. Macroscopic properties are known as state variables. The four most common macroscopic properties which are sufficient to define the state of the system are composition, pressure, volume and temperature. If these properties are fixed, all other physical properties of the system are automatically fixed. Thermodynamic equilibriums. A system is said to be in thermodynamic equilibrium if the macroscopic properties of the system in various phases do not undergo any change with time. In fact, the thermodynamic equilibrium implies three different types of equilibria which must exist simultaneously. These are, first one, thermal equilibrium. The thermal equilibrium demands that there should be no flow of heat from one portion of the system to another. This can happen if the temperature of the system remains constant. Second one, mechanical equilibrium. This equilibrium implies that no work should be done by one part of the system over another. Third one is chemical equilibrium. This chemical equilibrium demands that no change in position should be takes place in any part of the system with the passage of others. Next, nature of work and heat. As is well known, whenever a system changes from one state to another, it is accompanied by change in energy. The change in energy may appear in the form of heat, work, light, etc. Initially, the British physicist James B. Joule showed in 1850 that there is a definite relationship between mechanical work done W and heat produced H, that is, W is directly proportional to H or W is equal to JH. Here J is known as the Joule mechanical equivalent of heat. Its numerical value is taken as 4.184 into 10 to the power 7 x is equal to 4.184 joules. With the expenditure of 4.184 joules of mechanical energy, 1 calorie of heat is produced. This was one of the most remarkable experiments in physics. The statement of first law of thermodynamics. First law of thermodynamics is well-known definition, especially energy can neither be created nor destroyed, although it may be converted from one form to another. Another definition, the total energy of an isolated system remains constant, although it may undergo transformation from one form to another. third one, it is impossible to construct a perpetual motion machine, that is, a machine which would produce work continuously without consuming energy. Another definition is Einstein, the quoted is, Einstein in 1905 showed that the energy could be created by the destruction of mass. The energy produced E by the destruction of mass, m, is given by the equation E is equal to mc squared, where c is velocity of light. In the light of this idea, the law of conservation of energy has been modified, and now it is called the law of conservation of mass and energy. The mathematical formation of first law of thermodynamics. If heat Q is supplied to the system, it may be used up partly to increase the internal energy of the system and partly to produce some mechanical work. If delta E is increase in internal energy of the system and W is the work done by the system, then we have Q is equal to delta E plus W. So, while rearranging this equation, delta E is equal to Q minus W. If you change very small, it may be written as delta E is equal to del Q minus del W. If work done is the work of the expansion only and the volume increases by the small amount dV against the external pressure P, then we know that del W is equal to P dV. Hence, the above equation may be written as dE is equal to del Q minus B dV. According to the latest SI convention, as W is a negative, if work is done by the system, that equation 1 may be written as Q is equal to del E minus W, del E is equal to Q plus W. Heat capacity at constant volume and heat capacity at constant pressure. Heat capacity. The heat capacity of the system is defined as the amount of heat required to raise the temperature of the system through 1 degree centigrade. Thus, if Q is amount of heat supplied to the system and as a result of temperature of the system rises from T1 to T2, then the heat capacity of the system is given by this equation C is equal to Q by T2 minus T1. The temperature difference may be mentioned by delta T. So, Q by delta T. C is equal to del Q by dt. Heat capacity at constant volume simply mentioned by Cv. According to first law of thermodynamics, we know that del Q is equal to dE plus PdV. So, that it may be written as C is equal to del E plus PdV by dt. When the volume is kept constant, dV is equal to 0, and therefore, that equation 8 may be written as Cv is equal to dou E by dou T at constant volume. Cv is equal to, another format of Cv may be written as Cv is equal to dE by dt. For an ideal gas, this equation may simply be written as Cv is equal to dE by dt. Cv is the heat capacity at constant volume. The heat capacity at constant volume may be defined as the rate of change of internal energy with the temperature at constant volume. Heat capacity at constant pressure. When the pressure is kept constant during the absorption of heat, that equation 8 becomes Cp is equal to dou E by dou T at constant pressure plus P dou V by dou T at constant pressure. As we know that that the heat content or enthalpy of the system is given by H is equal to E plus PV. On differentiating with respect to temperature at constant pressure, we get dou H by dou T at constant pressure is equal to dou E by dou T at constant pressure plus dou V by dou T at constant pressure. Combining that equation 11 and 12, we get, or for any ideal gas, this equation may simply be put in the form of Cp is equal to dH by dt. Cp is the heat capacity at constant pressure. Thus, the heat capacity at constant pressure may be defined as the rate of change of the enthalpy with the temperature at constant pressure. The relationship between Cp and Cv. If volume of system is kept constant when the heat is ordered to the system, then no work is done by the system. the heat absorbed by the system is used up completely to increase the internal energy of the system. If the pressure of the system kept constant, when the heat is supplied to the system, then some work of expansion is also done by the system in addition to the increase in internal energy. If at constant pressure the temperature of the system is to be raised through the same value as at constant volume, then some extra heat is required for doing the work expansion. So, it may be written as Cp is always greater than that of Cv. We have following equation for Cv and Cp. Cv is equal to dE by dt and then Cp is equal to dH by dt. From equation 15 and 16, the difference between heat capacity of an ideal gas can be obtained by subtracting equation 15 from equation 16. So, we have Cp minus Cv is equal to dH by dt minus dE by dt. We know very well or well known equation in thermodynamics, H is equal to E plus PV. We know 1 mole of ideal gas equation, PV is equal to RT. From that, therefore, H is equal to E plus RT for 1 mole of an ideal gas. While differentiating this equation with respect to temperature, we get dH by dt is equal to dE by dt plus R, or otherwise dH by dt minus dE by dt is equal to R. Combining this equation 17 and 19, we get Cp minus Cv is equal to R. For 1 gram mole of an ideal gas, the Cp is greater than Cv by the gas constant R, that is approximately 2 calories or 8.314 joules. Joule-Thomson effect. This famous effect in physical chemistry, when a gas is made to expand adiabatically from the region of high pressure to a region of low pressure, the temperature of gas changes. This phenomena is called Joule-Thomson effect. If stream of gas at high pressure is allowed to expand by passing through a porous plug into vacuum or the region of low pressure under adiabatic condition, it gets cooled up appreciably. All the gases except hydrogen and helium were cooled when they were subjected to Joule-Thomson effect. Helium and hydrogen were heated under similar circumstances. Joule-Thomson effect is useful in the liquefaction of gas. A gas gets liquefied when it is cooled below its boiling point, or it gets liquefied when it is cooled below its critical temperature and then compressed. In both the process, the gas has to be cooled. For this purpose, Joule-Thomson effect is used. The gas which is to be liquefied is allowed to expand through a nozzle from high pressure region to a low pressure region. It gets cooled. This principle is used in Linde's and Claude process of liquefaction of air. Joule-Thomson effect can be applied only if the initial temperature of the gas is below its inversion temperature. Joule-Thomson experiment. The experimental techniques used by Joule and Thomson for deriving a mathematical relation between the lowering of temperature and fall of pressure of gas and expansion is illustrated schematically as below. Now we are having the diagram. So these two systems are separated by porous block. A tube is made of a non-conducting material, is fitted with a porous plug G in middle and two position A and B on the side as shown above. The tube is thoroughly insulated to ensure adiabatic conditions. A volume V1 of the gas enclosed between the position A and the porous plug G at a pressure P1 is forced slowly through the porous plug by moving the piston A inwards and is allowed to expand to a volume V2 at a lower pressure P2 by moving the piston P outward as shown. So work done on the system at the piston A is equal to minus P1 V1. Work done by the system at the piston B, P2 V2. the net work done by the system may be written as P2 V2 minus P1 V1. This expansion of gas has taken place adiabatically, that is, no heat has entered the system nor has left the system. Therefore, the gas performed work at the expense of its internal energy, that is, there will be a fall in internal energy from E1 to E2. So, simply that equation may be written as P2 V2 minus P1 V1 is equal to E1 minus E2, or otherwise E2 plus P2 V2 is equal to E1 plus P1 E1. We know that equation E plus PV is equal to H. So, based on this equation, H1 is equal to H2 or delta H is equal to 0. So, Joule-Thomson expansion is an isoenthalpic process, that is, adiabatic expansion of a real gas occurs at constant enthalpy. P2 V2 minus P1 V1 is equal to E1 minus E2. So, based on this equation, H1 is equal to H2 or delta H is equal to 0. The relationship between the fall in temperature delta T and the fall of pressure delta P based on the Joule-Thomson effect. Delta H mentioned earlier. The enthalpy of system is a definite property depending only on the state of the system. Taking H as a function of pressure and temperature T, it is possible to write as follows. H is equal to function of temperature and pressure. So, mathematically this equation may be written as dH is equal to dou H by dou P at constant temperature into dP plus dou H by dou T at constant pressure into dt. But we know dou H by dou T at constant pressure is equal to heat capacity at constant pressure, that it may be simply mentioned by Cp. So, dou T by dou P at constant H is equal to minus dou H by dou P at constant temperature by heat capacity at constant pressure. The equation 21 becomes dH is equal to dou H by dou P at constant temperature dP plus Cp into dt. Since, as discussed above, H is a constant in adiabatic expansion of a real gas. So, dH is equal to 0. So, dou H by dou P at constant temperature dou P plus Cp dt is equal to 0. The quantity of dou T by dou P at constant H is known as Joule-Thomson coefficient and is denoted as a mu Jt, assuming mu Jt to be constant over a small pressure range. So, equation 23 may be written as delta T is equal to negative form of dH by dP at constant temperature into dP del P divided by heat capacity at constant pressure, where del T is the fall of temperature produced as a result of the fall of pressure delta P, Joule-Thomson coefficient of an ideal gas. Since H is equal to E plus PV, so that equation 23 becomes dt by dP at constant enthalpy is equal to mu Jt, that it may be written as minus 1 by Cp dou E plus PV by dou P at constant temperature. So, while modifying that equation may be written as minus 1 by Cp dou E by dou V at constant temperature, dou V by dou P at constant temperature plus dou PV by dou P at constant temperature. For an ideal gas, dou E by dou V at constant temperature is equal to 0, and also for an ideal gas, dou PV by dou P at constant temperature is equal to 0. Therefore, that equation 25 becomes mu Jt is equal to 0. It is evident from the above equation that Joule-Thomson coefficient in an ideal gas is 0. Next, Joule-Thomson coefficient of a real gas. dt by dP at constant enthalpy may be positive or negative for a real gas. That is, when the pressure is decreased, the temperature may decrease or increase. If mu Jt is positive, decrease in pressure will result in decrease in temperature also. If mu Jt is negative, then decrease will result in increase in temperature. mu Jt depends only on initial temperature of the gas which undergoes Joule-Thomson effect. The temperature at which mu Jt changes, its sign is known as inversion temperature. That is, if gas is above T1, then mu Jt is negative. If the gas is below Tj, the mu Jt is positive. The relation between mu Jt and van der Waals constant. Joule-Thomson coefficient can be easily calculated with the help of van der Waals equation. Since both A and B are small, the term AB by V squared in van der Waals equation can be neglected provided the pressure is not too high. The van der Waals equation may be written as PV plus A by V minus PB is equal to RT. An approximation, we may replace V by RT by P. Therefore, PV is equal to RT minus AP by RT plus BP. This equation 28 is differentiated with respect to temperature at constant pressure. We get dV by dt is equal to R by P plus A by RT squared. Substitute that value of R by P from equation 27. T dou V by dou T at constant pressure minus V is equal to 2A by RT minus B. Now, utilizing the well-known thermodynamic relations, V is equal to T into dV by dt at constant pressure plus dH by Tp at constant temperature. dt by dP at constant enthalpy is equal to 1 by Cp dou A by RT minus P. It is evident from that equation 31 that Joule-Thomson coefficient is positive as long as 2A by RT is greater than B. It becomes 0 if 2A by RT is equal to B and negative if 2A by RT is less than B. Since B and R are constants, it is evident that magnitude and sign of Joule-Thomson coefficient depends only upon the temperature at which the gas is allowed to expand. Inversion temperature. The temperature below which a gas gets cooled during an adiabatic expansion is known as its inversion temperature. When a gas is subjected to Joule-Thomson effect, it gets cooled up appreciably. But when hydrogen and helium were subjected to Joule-Thomson effect, they were heated up instead of getting cooled. But very low temperature, these gases also get cooled. For example, hydrogen below minus 80 degrees centigrade and helium below minus 240 degrees centigrade behaved like this. Thus, we find that for each gas there is a particular temperature below which the Joule-Thomson effect is always cooling effect. This temperature is called the inversion temperature of that gas. At this inversion temperature, mu Jt is 0. So, 2A by RTI minus B is equal to 0. 2A by RTI is equal to B or Ti is equal to 2A by RB, where Ti represents the inversion temperature. Thus, the inversion temperature depends upon van der Waals constant A and B of the gas. Thank you.